Now, last but not least, I want to close the circle again and go back to VASCO, which we discussed at the beginning when we talked about the functional approach. And I want to show you again what really is the advantage of IFDS and IDE over this initial framework VASCO that I explained. Maybe you already got your head around this on your own by now, but I just want to make this crystal clear. So remember when we talked about VASCO, I showed you this particular example here, right? Where we wanted to summarize the effects of calling this callee procedure here. And we had different call sites where, in fact, the value I here had different valuations at different call sites, right? So at the one, we have the value 2, and at the other one, we have the value 3. So we really only have the difference in this value. And in fact, this value didn't really matter for the summary function here, right? Because this value is printed, but it's never returned, so it never has any effect on the caller, and therefore it never becomes part of any procedure summary, okay? So the difference does not really matter for, sorry, it does matter for foo, but it doesn't really matter to the main method here, okay? Yeah, nevertheless, so we need to reanalyze all of foo, including what happens to h, although that's really not important. And now when we look at how you can do this with IDE, you will see that there are actually some benefits here. So let's take a look at how this would work in IDE. So we would basically have such an exploded supergraph representation that you see here, and we would get these kinds of flow and edge functions, right? So here, j is being assigned the value of h multiplied by 2, and then k gets the value that we just have here, but 1 added to it, okay? And yeah, there's not much happening here, but essentially then we would be creating procedure summaries out of this, right? So you would then have basically a jump function, for instance, from here to there, that tells you that you obtain the value of k by taking the value for h, multiplying that by 2 and adding 1 to it. Okay, fair enough. But now the point, the point is that this is a summary that is applicable in both of these calling contexts here, right? So you can apply the same summary here, and you can compute it here and apply it here. So you would obviously once compute it, right? So the first time you actually see a call to foo, you would compute the summary and you would apply it to this calling context. But then for the second calling context, you would just apply that same summary again, right? So there's really no need to recompute anything here. You really obtain the summary reuse. And that's a lot better than what we had in VASCO, right? Because in VASCO, we did not actually have this property. The problem there was that just because the value of I changed, we couldn't reuse the summary, right? I mean, there was a summary, but we couldn't reuse it because this value had changed, and VASCO always matches summaries, as an entire atomic summary, you could say. So you can only match the entire summary or nothing at all. And here we can really match on the summary only for h, right? And we can reuse that part of the summary. Even though I changed, right? We would not have to reanalyze any effects for h, and that part of the computation could be omitted. And so that's really giving us savings here. And that's showing us how this can be superior to VASCO. Of course, the difference to VASCO is that you have to have a distributive problem for this to really work, right? So if you want to have a precise solution for a non-distributive problem like full constant propagation or a pointer analysis, for instance, then you are probably better off using VASCO, because if you want to force such a problem, into the IFDS or IDE frameworks, then you are deemed to have to do certain approximations. So just to recap, so here this really, this IDE framework, it really computes distributive summary functions, which are annotated to IFDS data flow edges, right? So we obtain these jump functions. And then callee side functions are constructed only once, but are re-evaluated in every context, right? So at every call side, we compose the call flow function, the summary, and the return flow function, and then we also merge this with the call to return flow functions. And like I also explained, this requires a finite representation of function composition and merge, right? So that's something that as an analysis programmer, you would actually need to implement. But opposed to IFDS here, we have this nice property that the value domain can actually be not just very large, but it can even be infinite. So all in all, IDE really, it really does add some substantial properties to IFDS. The class of problems that are solvable with IDE, it's definitely larger than the class of problems you can solve with IFDS. Yeah, and that actually concludes my lecture on IDE. And that also concludes everything I wanted to say on the matter of the functional approach. And it actually also concludes the sort of theoretical part that I had for this course. So there will still be another lecture where we are going to be talking about a few more practical aspects, in particular, what is a practical way of actually denoting flow functions in implementations. There are still some tricks that we want to explain to you. And then, in case you have enjoyed this course, which I certainly hope, you are very much welcome to also attend my course DECA 2, which will be happening in the next semester. There I will be explaining some more important concepts. So in particular, there has been recent work over the last 10 years or so of using push-down systems as sort of extensions to IFDS and IDE, which gives you also some interesting capabilities. We will also be talking about so-called demand-driven analysis. So this is a flavor of analysis that I briefly hinted at in this course already, where you are not analyzing the entire program as a whole, but where you're rather analyzing fragments of the program that really matter to you. For instance, because you already know through some lightweight syntactic analysis that at this program point, it's possible or even likely that you have a security vulnerability, let's say, right? Then you would want to have a very detailed demand-driven analysis of that program part and maybe not regard other parts of this program at all. And this requires certain algorithms, it requires certain data structures and tricks, and I'll be covering these in depth in DECA 2. As it turns out, if you have such demand-driven algorithms, they are not just more efficient, they're actually also more precise. I want to explain to you also situations in which you can obtain such added precision. And then also in DECA 2, I will be talking about many practical aspects and actual instantiations and implementations of such static analysis. So I will be covering concrete security analysis tools and also tools that support people who actually implement static analysis. For instance, there's a tool-based approach called Tamiflex that allows you to deal with reflective calls that if you don't deal with them, they might actually make your call graph unsound because it becomes incomplete. And we will be talking about FlowDroid, which is a very popular taint analysis approach for Android that implements a couple of tricks. And we will also be talking about other security analysis tools that we and others have built on top of these frameworks in the last few years. One other very popular one is called CogniCrypt. It's actually a very versatile tool that allows you to define static analysis rules on your own using a domain-specific language. And you can then use CogniCrypt to actually find misuses of APIs, in particular also of cryptographic APIs, hence the name. So for instance, you can find out if people have accidentally missed certain calls to an API, or whether they've issued these calls in the wrong order, or chosen incorrect parameters or parameter combinations, and so on. And all this is implemented actually using a demand-driven, context-sensitive, highly precise and highly efficient taint, and also taint analysis and constant propagation, and also type state analysis. So this really brings everything together that we have been talking about in the last few months, and it's really a nice showcase. And so if you listen into DECA 2 at the end of the course, you will really be able to construct such tools on your own. And you will have understood really the top state of the art into, about all these algorithms that go into these card tools. Yeah, so I'm very happy to invite you to listen into this. The course will start sometime in April. If you stay subscribed to my YouTube channel or regularly visit our website, then I'm sure you will get an update about it. So far, so good. I did not get to see much from your side, so I really hope you enjoyed the course. If you did, I would be very happy if you could drop me a note or just leave some comment. Also, if you found that there are certain parts to be improved, I'm always happy to accept your suggestions and maybe even some concrete changes to the slides. I'm always very happy about this, so please do let me know. Thank you very much. See you later. Bye-bye.